Hey, good afternoon, everyone. Welcome to the class. So, we started talking about waves, and then we said, okay, certain property of the light or the waves can be uh, dealt with by just assuming rays of light. Now we are coming back to the wave description of light. Okay, so the main phenomenon that basically tells us whether something is behaving like wave or not, we determine that by just looking at whether they are interfering with each other or not. Okay, so interference is the sure test of whether something is behaving like wave or not. So here what we see is this thin, like in this kind of thin film, we have this color, and that color is the result of the interference. So this is an example. So we'll talk about thin film interference next class. Today this is just an example, but we'll talk more theory behind the interference, which we kind of talked in terms of superposition of waves when we introduced the waves. So basically, we're going to build from there. Okay, and diffraction and interference, they are not that much different. We do deal them, about the same way. But when we look at something like this, so it's hard to see, like light diffracting. But you see here, what happens? Often we say, okay, the waves propagate in a straight line. But here we see when the wave passes through a small opening, it spreads in all direction like that. You see that? So it's spreading. So this spreading of wave is called diffraction. Otherwise, the wave here should be just going something like this if it wasn't, spreading, or if it wasn't diffracting. So the main difference here is that when we talk about diffraction, we have just only one opening. But when we talk about interference, usually it happens from two openings. So there are two identical sources coming and interfering with each other, or mixing with each other, superposing with each other. These are different words for the same thing. But what we believe is that these waves, basically, when they are propagating, they are emitting new waves. So there are always waves to interfere with. So even in the diffraction, there is this kind of interference going on. So basically, how we deal with them, how we describe them, gonna be about the same with very subtle difference. Okay. The main difference here is that when we're talking about diffraction, there is only one opening. And when we are talking about interference, we are talking about two openings. So I am just getting a message saying that the slides are not posted. So let's see if I can figure that out. Okay, so this interference and diffraction phenomenon, or the how we treat light as a wave, is called the physical optics. So what we did in last two chapters, or last two classes, or maybe, yeah, last two classes, it was like a geometric description where we kind of made triangles and so on, drew the line representing the rays of light and so on, right? So that was geometric. So when openings are larger, we can use geometric optics, but when openings becomes small, and how much small is small? So that is comparable to the wavelength of light. And light wavelength is very small. It is in the order of 10 to the power -7 meter. Okay. So remember 1 meter is thousandth of, so okay, 1 meter, we know 1 meter long scale. And then 1 millimeter is thousand, right? So 1 centimeter is hundredth of a millimeter, sorry, hundredth of a meter. And 1 millimeter is thousandth of a meter. So when we go from 1 meter to 1 millimeter, we know how small it gets, right? Now, think about dividing a millimeter into 1,000 parts and picking just the one small opening. That is a micrometer. So 10 to the power -7 means, like even tenth of a micrometer. So these are very small. So usually for most of the opening we see, those are not like a small opening for light, okay? So that's why even when we do our eyes very, like something like this, try to shut our eyelid all the way, uh, still we're not getting that in that range of the opening, okay? Still rays of light or the geometric wavelength or sorry, geometric optics works, okay? But when it gets even smaller than that, and there are devices that we use for that, then in that case, we have to use this physical optics or the wave description, okay? And that's what we are doing, okay? And that's where we get the interference and diffraction. And remember, this interference is the test, just like I said, is whether something is behaving like a wave or not. So if something is interfering, if we see interference phenomenon, that means that thing is behaving like a wave or not. Okay. So later we'll talk about the electrons, which are particle that has mass, right? They also interfere. They produce interference pattern. So what that means? Electrons behaving like a wave, not just particle. So they are behaving both like a particle and the wave. Okay. So that's kind of interesting. So this kind of idea helps us to understand the things better, how they behave. Okay. So now here is, for interference to happen, we need two sources, and two sources should be producing coherent wave, we say. So what that means? When they have same frequency, okay, and similar phase relationship, when they move. So for example, they were there, and see the peak was lining up with the peak here, right? And then both of them move the same distance. And when they did, the peak and peak are still lined up, trough and trough, they are still lined up. So we say, okay, that means they are maintaining the fixed relationship. Okay. So we say, okay, phase difference between these 2 points. See, this is also at the peak. This is also at the peak. So we say phase difference in this case is 0 between these two waves. So now when we have coherent wave, two coherent waves, and when we mix them, when they arrive to the same point, they can mix up three different ways we talked about: constructive interference, destructive interference, and then partial interference. So here I am basically repeating the same thing, but with a little bit more detail. Okay. So what you see here is a wave represented by blue wave, another one is represented by kind of red wave, right? Kind of brown wave, red wave. So what happens if we look at here, the trough of this one is matching with trough of this one, peak of this one is matching with peak of that one. So that means what's happening is we say, okay, when they overlap that this way, their amplitude, see, amplitude is the maximum displacement of this wave position from the mean position, right? So that's amplitude. So their amplitude, let's say if they have same amplitude, then what happens after mixing, after adding, the amplitude becomes double, okay? And frequency remains same. So when does this happen? So we can write this condition, constructive interference condition, two different ways. One in terms of phase difference, another in terms of path difference. Okay. And this path difference and phase difference, they are related. So I'll talk about that. And this is important to understand this and whole interference and diffraction. So if you will, please pay 100% attention here. Okay. So when something is, let's say, at the peak over here and reaches, comes down and then reaches to the peak. So it's like saying our pendulum is oscillating and it's oscillating from one side here and then goes to the other side and comes back to the same side. So it's like saying pendulum is in one side, goes to the other side, opposite side, and comes back to the same position. Okay, basically. So this separation distance between this peak and peak we call wavelength, right? So we learned that. And now what happens is, since it went through one complete cycle, and one cycle is equivalent to 360 degree, and in terms of radian, that is 2 pi radian, what happens is, in terms of path difference, this is equal to wavelength. So what's the difference in terms of position here? One wavelength, and that is equivalent to one. What's the phase difference? Equivalent phase difference, that's a one cycle, which is 2 pi radians. Okay, so that means these two are equivalent. They are not same, but they are equivalent. Okay, so now what you see here is that when does the constructive interference occurs? If we want to write that in terms of equation, what do we do? See, the phase difference, this notation, and usually we use this phi symbol for the phase, and phi phase is nothing but the fancy language, fancy word for the angle. So just like we said, in one complete rotation it goes through 360 degree or 2 pi radians, right? Similarly, we can say, okay, when it goes to the half cycle, from one extreme of the pendulum to another extreme of the pendulum, when it does that, then in that case, what happens? It is half of 2 pi, means it's just pi. And then now when it is at the quarter cycle, then this phase is pi over 2 and so on, right? So now here, one wavelength is equivalent to 2 pi, means half wavelength is equivalent to, not equal, but equivalent. So that's why I'm writing 3 equals 3 lines here. Lambda over 2 is pi. Lambda over 4 is equivalent to pi over 2, because this is quarter cycle. In terms of angle, that quarter cycle is 90 degree or pi over 2 radians. Okay, so that's how it works. So now, to write condition for constructive interference, when does the constructive interference happens? To write that in terms of equation, so in terms of change in angle or phase difference, how do we write that? it is 0, the m times 2 pi, where m are the integer numbers. So m is 0, 1, 2, etc. Okay. So what that means, let's see. Here we have a point and we have another point. The phase difference between these 2 points is 2 pi. So if we look this way, starting from here versus starting from here, they are equivalent. They are just repeating the same thing. It doesn't matter whether you start from here. This is sine wave starting from here, for example. And at 2 pi, what happens? Same thing. It starts going down. Here it's doing the same thing. It's repeating the cycle. So by changing the phase difference by 2 pi, we're not changing the wave. So because of that, what happens is when they overlap, they always meet the peak with the peak, okay? And trough with the trough, and so on. So that's why they go through this constructive interference. And in terms of path difference, for example, delta x, delta r, sometimes uh, that may be written delta L, okay, different notation you may see. But here I'm writing delta x. So this is one wavelength, and in terms of wavelength as well, it is doing the same thing. So that means this 2 pi radian is equivalent to lambda wavelength, or one full wavelength. So that means we are just doing that. So multiply that m by either full wavelength or 2 pi phase, 2 pi radian phase, keep that in mind, 2 pi radian phase, and the result is equivalent, and that gives us constructive interference. So m is equal to 0 means phase difference is 0. And if I look at this point and this point of these two waves, that means phase difference is 0. Okay. And we can have phase difference between 2 points of 2 waves or the same wave. Okay. So for example, we can look at the same wave. And for example, if I look at this point here and this point here, just like I already said, the phase difference here is quarter cycle or pi over 2 radian. Okay. And between this point and this point is pi radian, and this point and that point is 2 pi radian. And similarly, we can also compare the phase difference between two coherent waves. So for example, this point and that point, see, this is, crest, and this is also crest, mountain, and mountain. So that means we say, okay, phase difference between them is 0. And now if I look at this point here for this blue wave here, and now if I look at this point here for this wave, then there is a phase difference because this is peak and this is valley. So the phase difference is exactly opposite. It has inverted phase, opposite phase. Opposite phase means 180 degree pi radian. Okay. So that's how we can write the phase difference between two waves or even the same wave, 2 points at the same wave, or 2 points in the two different waves. So that's how this phase difference and path difference happens. So if you totally want to understand the interference and constructive interference, understanding what's going on, what this means this wave, if it is, like right now, if it's overlapping something like this, if I were to move this wave by this much, then what's going to happen? This peak going to overlap with this one now rather than overlapping on that. And the result going to be same. So that's what that means. And same thing goes with in terms of wavelength as well. Okay, folks. So that is constructive interference. Okay. Now, when we have constructive interference, amplitudes gets added. So if both of them have same amplitude, A and A, it becomes 2 times A, just like I have shown here. But they may not have same amplitude. They can still interfere constructively when that happens. So this C subscript here, I'm just writing for constructive interference, and that's that. And we looked at this equation before as well. So if I want to see the interference pattern, what I'm looking at is bright and not so bright spots. So brightness comes from intensity, and intensity of a wave is directly proportional to the square of the amplitude. So that's why I am squaring this equation on both sides. Okay, so it's like squaring this A plus B thing squared, right? When we square that, so that means the result is that the first one is squared, second one is squared, plus 2 times first and second, right? So now, using this idea that amplitude is squared is proportional to the intensity, we can replace this by intensity of the resulting wave, and this is just the intensity due to first amplitude, this is intensity due to second amplitude or amplitude of second wave, and then this is the combination. So combination is coming from this term here. Okay. So that algebra showing you, hey, the interfering term is this. So this has the effect of increasing the intensity. So we can write something like this. So since I is proportional to A square, what happens? A is proportional to square root of I. So that's why when we have just A1, we have just I1 under the square root. Okay. So by how much the brightness increases, we can tell by just doing this. And you have seen this equation. You have done exercise as well, I'm guessing, using this equation when we talked about superposition of wave. So basically that's what that is. So new thing is I hadn't introduced this equation. So now I'm introducing this equation, and this is important equation to analyze. So this is for constructive interference. Okay, but we can have destructive interference as well. When does that happen? When the peak and valleys are lined up exactly. So when do they line up exactly? See here, the peak versus valley, they have phase difference of pi radian or half of wavelength. Okay. Remember, this whole thing is one wavelength, means this is half wavelength. Okay. So either phase difference is pi radian or path difference is this. Okay. So now, first destructive interference happen when, let's say, you move the wave and now the waves are like facing opposite. Okay, that's where the destructive interference is. You see here, the peak lines up with the valley over here. Peak of this blue wave is lining up with the valley of this one here. So if this has amplitude negative A and this has amplitude positive A, so what happens? When we add them, positive and negative, they have canceling effect. When we do, we say, okay, that is destructive interference. So mathematically, how do we write that? So we need to shift it by pi, whatever we had before. So we had this in the previous slide for constructive interference. We had this. Delta pi is m times 2 pi. That's what we had. Now, what we have to do is, see, we are shifting it by pi. So that means we need to add that pi in this equation on this side. So that has to be the phase difference. And usually what you see is it's written something like this. So if I do this 2 pi and this is 2, see, I can factor this 2 pi from here like this. So that's why you have m over there and then this half over there. Okay, so basically same thing. And since 2 pi is equivalent to 1 wavelength, we can write that in terms of wavelength as well. So now Again, what's the values of m's? So 0, 1, 2, 3, and so on. So for example, for m is equal to 0, what happens here? When I put m is equal to 0, so let's say when I use m is equal to 0, that means this becomes 0. So delta pi is exactly equal to pi, okay? Or half of 2 pi means pi. And that's the difference you see, okay? So now, what if I put m is equal to 1? Then when I put m is equal to 1, for example, then this is going to be 1 times 2 pi, means 2 pi, and then plus pi is 3 pi, okay? So now the destructive interference is going to happen when the phase shift is 3 times pi, okay? So looking at here, where do we find 3 pi? So over here, from here to here, one wavelength is 2 pi. And over here, this is 4 pi, next peak. So that means over here is going to be 3 pi starting from here, okay? And now you see this 3 pi difference is lining up with this. So here there is a valley and there is a peak. And peak and valley again matches when it shifts by 3 times pi. So it has to be pi, 3 pi, 5 pi, and so on. When the phase difference is like that, then destructive interference. But when phase is 0, 2 pi phase difference is 0, or 2 pi, or 4 pi, and then in that case, what happens? Constructive interference. Okay, so by just looking at how the phase difference is going to be, we can tell, hey, at that point it's going to be constructive interference, bright spot, or destructive interference, not so bright spot. So for example, here the amplitude became 0 because this has a positive A and this has a negative A. So when we add them, it becomes 0. Okay. And mathematics for doing that is either this or that. So if we have to do in terms of phase difference, we write this condition in terms of angle, right? If we have to do in terms of path difference, in terms of length, then we write this equation. Both of these equations are not same, but they are equivalent as long as you can remember 2 pi radian is equivalent to 1 wavelength, you are good. Okay, so now just like we did before, we can also write the equation for intensity. Okay, so here what has to happen? A1 minus A2, we have to square that. Okay, and we write like that, and no matter which one is bigger, it's just the amplitude, so we just square the modulus. Okay, so here these two terms are still positive, but this one is negative. So for example, if two waves have same amplitude, like in this case, we have A for this, and this one also has the same height, so we can say A. So in that case, what happens to the net amplitude? So in that case, for example, if I were to calculate A square, then this is gonna be, hey, should I say destructive here? I think I did not put D subscript. A square, AD square, gonna be A square plus A square. Why? Because this one is A, so A1 is A, A2 is also A. So that means we have, for A1 square, we have A square. For A2 square, we have again A square. And then now 2 times A1 is A and A2 is also A, means this becomes 2A square. And if you add them what happens? It becomes 0. Okay. So this a square plus c square minus 2 times a square becomes 0, and that's the result. And similarly, we can get the intensity 0 as well by using that intensity equation. So this is like constructive interference. However, this has a negative sign now for the destructive. Okay. So that's how it turns out. Okay, this was kind of a little long
I have a
rant.
before we move on. So is this basically the same concepts as sound waves
Yeah,
through?
all waves basically. Yeah,
Okay.
sound wave also goes through the constructive and destructive interference. Actually, I have an example here later, about the speakers. So yes, that's a good question. So now, here is a question for you, and turns out I haven't started clicker. So go ahead, you start your clicker if you haven't, and I'm doing that too. I need to update this one as well. Okay, so I'm opening the poll, and you have a minute and 30 seconds for this one being first one. Oh, 30 more seconds. Five more seconds. Five, four, three, two, one, and it stops. Okay, let's see what we got. So we got all of them. Bit more for D. So for constructive interference, what did we wrote, about the phase? Delta pi is m times 2 pi. That's what we wrote. And we said m is 1, 2, or it can be 0 as well. 0, 1, 2, 3, etc. So now, so that means it is like saying, okay, phase difference is 0, or could be m, when we m is 1, it is 2 pi, and when m is 2, it is 4 pi, and so on. So what do we see here? So basically this 2 is making this m only even, right? So 2 times odd, even the odd integer becomes even, right? So we are getting 0, 2 pi, 4 pi, and so on. So there is one response, 0. That sounds correct. But in this case, it says a general condition. So this is one specific condition. Okay. So this is more general. Looks like this one is better. If this wasn't there here, and then this could be answer. Okay. So that was close. But better is this. See here, even integer multiple. So 2, 4, 6, those are even, right? So that's how we can write it. Okay. So looks like D is correct answer in this case. So that is for constructive. Now, how about destructive? So I'm now opening the poll and similar question, similar choices, but this time it's a destructive. Let's do 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got here. We have odd integer multiple of pi, mostly. So let's see. So we have delta pi is m plus half 2 pi. So that's what the equation is. So when m is equal to 0, let's do for a couple of these. So delta phi is when m is equal to 0, this is half of 2 pi, means it's just pi. And then when m is equal to 1, then this becomes 1 plus half is 3 half. So 3 half times 2 is 3. So that means 3 pi. And you can now guess it's going to be 5 pi and so on. So only the odd integer multiple of pi. So yes, E is the correct choice. Okay. And by the way, so integer means it could be negative or positive integers. Okay. It does not have to be just positive integers. So keep that in mind. So it can be other side as well. So when we start counting, see this wave may be going from all the way both side. My drawing is not that great here. So if we say this is m is equal to 0, then we can say, okay, this is m is equal to -1 on the one side, and m is equal to +1 to the other side. So any integer, positive or negative, are valid for this, okay? Constructive and destructive both. So now here is a video. Let's see if we can.
Okay, I'm going to demonstrate what happens if you connect up your speakers wrong in your home stereo or home theater system. It's important to connect the red lead to the
I know these days we have HDMI connector or even the USB-C connector, but we used to have, and I guess we still have some of these, connected something like this. So red and black.
red jack and the black lead to the black jack in the same way on both speakers. Your leads may not be, your speaker wires may not be colored red and black, but often they're colored positive on one of the wires and then unmarked on the other, or some different color. You want to connect them up to your speakers in the same way for the following reason. What I've done here is I've got two speakers that are actually facing each other, so their cones are vibrating this way, and I've connected up the speakers correctly so that both speakers are in phase, meaning that the same signal fed to both speakers causes this speaker to move out at the same time that this speaker moves out. So they're moving out or toward each other, and then away from each other, toward each other, and away from each other. And that causes large compressions and refractions and a loud sound to be emitted. This is a 100 hertz sound, 100 cycles per second, that is produced with these two speakers oscillating in phase. So if you instead connect them up wrong, and you connect the red to the black, and the black to the red, with no change to the signal, then you get a much softer sound. Why is that? It's because this speaker is now out of phase with this speaker. This one moves out away from itself. At the same time, this one moves in. And so they're moving back and forth this way, and they don't push as much air around. So then back one more time to the in-phase correct arrangement. You get that louder, more satisfying sound. So it's important how you connect. Okay, I'm going to demonstrate.
So I think I have another video that shows the constructive and destructive.
Okay, this is a demonstration of interference patterns produced by two speakers. This signal generator is generating a tone that's at about 2,000 cycles per second, 2,000 hertz, and it's sending the same signal to both of these speakers. And if you're out in front of those two speakers, then what matters is the distance from you to one speaker compared with the distance from you to the other speaker. If those two distances are the same, then the sounds that are produced by these two speakers overlap and interfere constructively. They add together to form a louder sound. But as soon as you've moved a little bit in such a way that the wavelength, that the difference between the two paths, between one speaker to you and the other speaker to you, is half a wavelength, then instead of the peaks and the valleys overlapping with each other, you get a peak where there's a valley in the sound, and the sound cancels. That's called destructive interference. And so what we're going to do next is to use this microphone attached to this meter and move through the sound field, and you'll be able to see with your eyes on the meter the level of the sound, as well as hear the sound picked up by this microphone that shows this constructive and destructive interference pattern. Okay, right now we have this microphone that's picking up the sound from those two speakers, and we're right symmetrically located in the center between.
So if we were to draw a line from this speaker to this meter and this meter to this speaker, these lines should have same length. Okay, so that means this wave traveled the same path as this one. Okay, so because of the camera angle here, this line looks longer than this one. Okay, because of the camera angle, but based on what professor is saying, is at the middle.
The two speakers. So what we'll do now is to move away from the center, and this readout here gives the loudness of the sound that's picked up by this microphone. And as we move through the interference pattern produced by these two speakers, you'll be able to both hear the sound from this microphone, which will be louder, then softer, then louder again as we move through constructive interference to constructive destructive interference. And then you'll also be able to see that that the readout will show that loud, soft pattern. So I'm going to be quiet now so that the microphone will just pick up the sound from the speakers.
It was softest, it was softest, and then now increases, and again that's the destructive over there, and again looks like that's a maximum. So constructive fully, and again back to destructive, and so on. And it's for the sound we can hear and see, and a light wave we can set up experiment something like that to see the bright and dark spot over there. Here louder sound versus a not so loud sound, right? In case of light,
Okay.
we have both. So here is a problem related to what we just watched in the video. Okay, so here it says two speakers are 3 meters apart. So let's say there is speaker number 1 and there is speaker number 2, and distance between them is 3 meters, 3.0 meters. So it looks like this problem is two sig fig problem. Play identical tones of frequency. F is 170 hertz. You stand directly in front of one speaker at a distance of 4 meters. So one of the speaker. So let's say you are standing directly in front of one of the speaker, and this distance is 4 meters. Okay. So here observer, that's you. Is this a loud spot or quiet spot? So one way to figure this out is to bring that microphone and meter and listen, right? But we don't have to do that. We can just figure this out by just using the condition of constructive or destructive interference. Okay. So now, so that means we are looking for loud spot. Means is it so constructive, and quiet spot means destructive. So that's what we are trying to figure out, whether this at this point the interference is constructive or destructive. So for that, what we have to do is we need to look at the path difference. So over here it went through 4 meters, right? X1, and this one, oh, looks like projectile. This one, X2, let's say, oh, how much is X2? When you add 3 and 4, what happens? It's a right triangle, right? Using Pythagorean theorem, we know 3 plus 4 is 5. So it's a 5 meter. So that means path difference we can figure out is X2 minus X1 means it is 1 meter. So now we learned that the sound wave went through 1 meter path difference. So now in 1 meter, whether it's going to go through constructive or destructive interference, we need to be able to write this in terms of m times wavelength. Okay. Or m plus half wavelength. So if this 1 meter is m times wavelength, then it is constructive. If it is m plus half times wavelength, then it is destructive. So for that, we need wavelength of this wave. But frequency is given and the speed is given. Okay, wavelength is not directly given, rather it is given indirectly. Okay, so that means we know for any wave, it could be light or sound wave, V is F times lambda. If it is light wave or any electromagnetic wave, we know this V is c, speed of light, but this being that, so we write V for the sound or any other speed other than the light speed or electromagnetic wave speed. So wavelength is, so here we need wavelength, so that's why I am going here and calculating wavelength. So wavelength is V over F. So V is 340 meter per second and F is 170 hertz. So that means 1 over second. Hertz is 1 over second. So what do we get? 170, 340. I think it's exactly double. So this is 2 meters. Okay. 2.0 meter. So that means delta x is half of wavelength. See, it is 1 meter we found, right? Delta x, we found 1 meter. But here, wavelength is 2 meters, means this path difference is half the wavelength. So now, so when we have this condition, is it satisfying this or this? Means constructive or destructive? Can we tell now? Right, so it is a situation when m is equal to 0, we get exactly half wavelength. That means half wavelength is destructive interference. So this is a condition for destructive interference. Therefore, it's a soft spot.
Dr. Ramesh, I have a
Yes.
question.
Yes, go ahead.
Oh, okay. So I understand how you got to 2 meters. I'm just not understanding how you figured out if it's constructive or destructive.
So you got 2 meters delta x, or let's say you are saying if we got 2 meters.
For the wavelength.
So for the wavelength, if this number was 1 meter, you are saying?
Yes.
If this was 1 meter, then yeah, that's a good question. So that means delta x would have been what? 1 times wavelength, right?
Yes.
If it was 1 meter, right? And this is exactly 1 meter, means this is 1 times wavelength. So when we have 1 full wavelength, that is like a m times wavelength, 1 times wavelength, right? So that means it would be constructive.
Oh, okay, that makes sense. Thank you.
Okay, I'm glad you asked. Hey folks, so anything else? And looks like this is exactly 3 o'clock. So let's take a break, and if you figure out any question, you can ask me after the break as well. I'll leave this slide right there. Okay, folks, so welcome back. Any question on this one?
I have a question.
Yes.
So when we get these problems, are we always assuming that the wavelengths are both in phase with each other
Uh,
instead of
when they start,
Mhm.
yes.
Okay.
When they start, yes, because interference, we usually do that with a coherent source. Okay.
Okay.
But over here, of course, it could be in phase or out of phase, and that's what determines the constructive and destructive, right?
Okay. Okay, thank you.
And I also have another question. So if we had 1 meter for the wavelength and we do 1/2, that will give us 0.5. So technically it's still 0, which makes it a constructive, right?
See, we don't do this, like divided by 2 all the time. Here I did divided by 2 because this 1 meter, we had this difference 1 meter, and wavelength we got 2 meters. So that what I'm saying is 1 meter is half of this 2 meter. So that's what I'm saying here. We don't always do half, okay? Here, 1 meter, and if wavelength is, if wavelength is 1 meter and this difference is also 1 meter, that means that is full wavelength. So we don't need to do half. Here I'm showing you the 1 meter is half of 2, okay?
Okay. Thank you.
Okay. So that, see here we got a number, but we need to convert that number in terms of wavelength, okay? So is 1 meter how many wavelength? 1 meter is how many wavelength? We need to write something like that. So 1 meter is half wavelength, and that's what I'm writing. And I try to explain by writing this, and looks like that even confused, okay? That was a bit confusing, I guess. So whatever number you get here, you compare that with the wavelength and see if it is exactly integer multiple or other way around, right? To see the constructive or destructive. So that's how we figure that out. Okay. Anything else? Okay, let's move on then. I have another video.
This is a demonstration of the pattern you get when you send light through 2 slits. In this demonstration, I've got a laser here. I'm sending it through 2 slits that are separated in the first case by 0.25 millimeters, and then in the second case by 0.5 millimeters, larger separation. In both cases, each of the 2 slits is 0.04 millimeters wide. So what you see now is the pattern produced by this 2-slit pattern. And you can see a big bright spot here, but I'm hoping you'll be able to see that there are small divisions, maybe 10 or 12 divisions within this big bright spot. Those are produced by the fact that we have 2 slits, interference, both constructive interference and destructive interference through this region. You can also see it divided out here in the other bright spots. So if we move to doubling the separation to 0.5 millimeters, then a wider separation means tighter spacing between those interference fringes. So you may or may not be able to see on the screen now that.
So let's do, let's look at first one here. So that's how the first one looked. So since we are on the screen here, I'm marking something like this, right? So that's how wide the central was here. Now let's look at the another situation here. So now what we see is this thing became a little bit, let's say narrower. So I don't know if they moved the distance of the screen. I hope they did not, okay? What we see is the pattern here. This is bright, big bright spot, let's say. And then there is a dark spot. And then brighter spot here, and then dark spot, and bright spot, and so on. So that means here, this is overall constructive and central and constructive. And this is exactly in the middle of those two. The waves are arriving exactly at the same distance. So for example, if those slits, for example, one was here, another one was there. So this is at dead center. That's what it is saying. So now this spot, what's happening? It's traveling. One of the wave is traveling longer than the other one. So how much longer? We learned that if it is half wavelength, then it becomes soft spot, right? So it's like for the sound, it is equivalent to soft spot, right? So this must be half the wavelength of the wave, okay? The path difference here. So this one traveled this much, this one traveled that much. If I draw a perpendicular line to that, so this is how far this wave had to travel more, okay? And this must be half wavelength, knowing that this is dark spot, okay? And now this is the next bright spot happen. So that means, of course, they travel different distance. And this one traveled that much, right? So now what's the difference? This difference, see, this went from bright to next bright. So this is like saying peak to peak. So this must be the path length must be equal to one wavelength, okay? And something like that. So that's what I wanted to show you with this one. And here is the drawing to represent something like that, okay? So what happens? This was first done by a gentleman, I guess, named Young. So Young Thomas, I think. But anyway, so two openings are here. And then this wave is coming. And once they enter, these two opening acts like a two source of the light wave, okay? And then they start generating their own wave pattern, okay? So go something like that. And depending on how far they have moved, so for example, here we see the dark spot. So that means this one and this one, if I look at here, if I look at this, so since this is dark fringe, dark spot or soft spot, the wave must have gone through the half of the integer multiple, right? Here we see the central bright spot, and of course this is not actual this is not actual picture, of course, it is just the drawing, I found a code somewhere and then I modified this for our purpose, okay? So that's that. So what you see here, excuse me, at the center bright pins, if we were to plot intensity, that's where it's the maximum intensity, and that is denoted by this big amplitude of the intensity here. And then path difference here, I am writing delta R, and I think before I wrote delta X, okay? Here I'm writing R1 and R2. So that's why the difference is delta R. So that's the path difference we are looking at, okay? So there is this, and then it turns out if we look at this triangle here, assuming this angle is theta, and where is that angle coming from? See, the one that's going in the middle, you know how far it is versus wherever it was in the middle. So for example, this angle theta is coming here from something like this. This is middle line, that's where the bright is. If I'm looking at this dark, then I'm going like that. So that means I'm looking at this angle as a theta. Okay, so that's what that theta is. So this theta, and using this D, which is the slit separation. So remember how that professor was saying 0.5 millimeter versus 0.2 millimeter or something like that. Okay, so that's what this is. So we say, okay, that is the slit separation. So if we use this triangle here, so I'm drawing this perpendicular line here so that this length, this path, and this path, they are same. So the difference in path is this much. So this difference in path becomes the opposite side of this right triangle. And we know opposite side of a right triangle picks up the sine. So that's why it is d sine theta. Okay, this d times sine theta. So this path difference can be written as a d sine theta. So now here a lot of things in this diagram. So this path difference, half wavelength, wherever there is half wavelength, this is dark. Wherever this is full wavelength, we saw in the problem, right? So wherever it is 1 times the wavelength, it is bright. And then whenever it is 3/2, and then it is dark. And it happens on the both side, means, you know, both side of the center. So if we are using positive to denote these, then we can denote these as a negative as well. So same thing happens here, half the wavelength on the negative side, full wavelength on the negative side, and this negative and positive simply one side versus the other side. And there is not much meaning than that other than that. Okay, so that's how we decode, or that's what we see. We looked at the video, we watched the video, and we have this drawing. Okay, and we have a little geometry here and trigonometry that gives us how much path difference is. Now by using this path difference, we can write equation, right? So this d sine theta, whenever d sine theta is m times lambda, that is constructive interference. So constructive means bright. And then for the dark, d sine theta, this path difference has to be m plus half times lambda. This is destructive or dark fringe. So that's how we can analyze them. And we can also look at, okay, this is center here, and how far this fringe is, right? So we may say, okay, along the y direction. So this is 0th fringe, and this is first bright fringe, and this is not first second bright, but this is second dark fringe, right? And so we can look at how far these are by finding the value of y here, by making triangle like this, okay, using the triangle like that. We can use that. how far it is. And also we can find the separation distance between, let's say, one dark to another dark on this side. So that's going to give us the width of this bright fringe from the center of this dark to center of this dark. That is like a width of this brightness. Okay, so we can use that, and this is called fringe width. Okay, this is called fringe width. So in the video, what you saw was the opening was very large compared to the wavelength of the light. So that's why the interference pattern wasn't that great. But if we can make those very small, and usually that's done by using what's called diffraction gratings, and that is also kind of interference. So in that case, what we see is we see a better separation of those bright and dark fringes. Okay? So how far a fringe is and what is fringe width and so on. So we're gonna talk about that, and I have also done that in detail in the note. Okay. So now here is a question for you based on what we just talked about. So going back to this diagram, just in case if you are having a difficulty understanding question, see the angle of this one and that one was this, let's say something like that. Or if we talk in terms of just theta, so it was this, right? So now what it is saying is it made this D double. Okay, so now opening is here, here, right? So here this was D, now it became 2 times D. Now how this width gonna change or this angle gonna change? Okay, so that's what this question is asking. So we'll do 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so now let's see what happened. We double the D. So the correct answer, so many of you chose D, but there are other choices as well, right? So how do I do it, right? So it's the same light. So this is the wavelength of the light. So unless we are changing the light or color, which we are not doing, right? Nothing else is changed. And so we did not do that. And we are looking at the same separation from center to the, let's say, first here, right? We are looking at the same angle in both situation, right? So this is same, means constant. This is constant. And this is also constant, same means constant, not changing. So what changed? This one changed. So to keep the result same, so we are multiplying two things here, D and sine theta, and for a small angle, sine theta is close to theta, so I can just write theta is m times lambda. These are constant. So when I change one, another one must change to keep this constant. it's like saying, okay, let's plug in number. Let's say this sum is some number, let's say 16, right? And let's say this was 4 times 4. Now, let's say if you double D, means you made this for 8, okay? Double. So for this to remain constant, 16, what has to happen to the 4? It has to be half now, otherwise it wouldn't be 16 or fixed, okay? So that's why it has to be half. So yes, D is correct answer in this case. Okay, so now let's talk about Fringe position here. So let's suppose this is center, right? This is center, and some of the, could be first bright fringe from the center, or second bright fringe, or could be any number, okay? So that's why I'm writing M here. M could be first. If it is first one, 1, then that means we're talking about this. If M is equal to 2, then we're talking about somewhere here, and so on, okay? So this could be any. So that's why I'm writing in general, okay? So if we know this is, let's say 0, and this is first, then we can say, okay, M is equal to 1. But if this happens to be fourth one, then we can write M is 4, okay? Whatever that is. And that length, that position is, I'm saying, okay, that is ym. And for these different values of m, theta gonna be different. So maybe we could even write sine theta m is ym over L, okay? So why am I writing something like this? Ym over L. So L is this distance here, separation distance between the screen and the slit. And this is the position of bright spot, or could be even dark spot we are interested in. But since we are, measuring from the center, so most likely we are looking at the bright spots here. So whatever it is, this length is like a opposite, and this length is like a adjacent and opposite. So adjacent and opposite. So opposite divided by adjacent is tangent theta. Okay. But when theta is small, and remember it has to be small in radians. It doesn't have to be in degrees. So for example, just like in case of pendulum, I don't know if you remember from physics 1, I said, for pendulum, the angle could be all the way to the 20 degree, okay? And still that can be thought as a small angle. So same thing goes here as well. We're talking in terms of, radians here. So in that case, what happens is sine theta is nearly equal to tangent theta. So this is also called small angle approximation. So we can write sine theta very close to tangent theta, which is also very close to theta, and it has to be in radians. Okay, theta has to be in radian. So anyway, so that's why I'm writing sine theta ym over L. Why am I writing sine theta? Because our equation has sine theta in it, and I want to replace this sine theta with this so that I can relate this with the wavelength. Okay. So I replace sine theta by ym over L. So when I do that, now we can clearly see how changing one gonna change the other things and so on, okay? So where is it? The bright fringe, let's say if I wanna know, then I can find that by solving for this ym, how far it is from the center, right? And by rearranging this, I get this equation. Okay, so it is position, And we can also find the difference in position between two, like let's say from this to that one. So I can find that and I can write that something like this. So if m is equal to 0, then it is like a y1 and y0. That means between this 0th and the first one, maybe I should be marking here, 0th and the first one, okay? But let's say if you use m is equal to 1, and that means it's going to be y2 minus y1. Again, this difference is this width I'm talking about, okay? Fringe width, that's what called fringe width, and that's what I'm writing. So difference in position between two fringes is fringe width, okay? And we can find that by using this equation. So if I plug in that one here, for example, for first one, for m, I have to use m plus 1. So this is going to be m plus 1 lambda L over D, okay, for this one. And for this ym, it's going to be just that. So it's like m plus 1 lambda L divided by D, and then minus lambda L divided by D, m lambda. It has to be, this is ym, so it has to be m lambda, this, exactly that, okay? So what happens when I open up, this becomes m lambda L divided by D plus 1 lambda L over D. So this m lambda over D gonna cancel with this -1, leaving us 1 times lambda L over D, and that's what that is, okay? So that is the fringe width. So fringe width depends on what? How far the screen is. Farther the screen is, farther these gonna appear, okay? And longer the wavelength, the farther they're gonna appear. But shorter the, larger the, so in this case, what happens? Let's see. So if the value of D becomes larger, then the fringe width becomes smaller. Separation distance and fringe width kind of becomes smaller. That's what it is saying. It's inversely related to the D, the slit width. Okay. Smaller, by making slit width smaller, you can separate them further. And that's what the previous question was about. It was in terms of angle, but the angle is related to this y, so we can think in terms of y as well. Okay. So now here is a question related to that. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so what we got here? So we got A, B, and C. Nobody got D. Bit more for C. So let's see what's in C. So what would cause the separation of the adjacent minima or maxima? They are kind of, if the adjacent between the maxima changes, minima also gonna change because they are just repeated pattern, alternative pattern. So when D increases, oh, what would cause the separation between the minima means what would cause the increase in delta y, which is between the minima is the fringe width of the maxima, right? So if we increase L, that's going to increase. Okay, so that makes sense. Okay. Now increase the separation distance between the slit. If you increase D, then delta y going to be smaller. So that's why this is not correct. And this one, for this one, we have to write this a little bit more. So C and B is F times lambda. So frequency is same, means when N, what it says, index of refraction of the medium increased. So that increased means wavelength decreased. Okay. So refractive index increased means wavelength decreased. So if wavelength decreases, then delta y gonna not increase, rather decrease. Okay. So looks like, yeah, C is the that. So yeah, C is obvious to see here. So that's how you use that formula, okay? Now, that is interference. Now, we're going to talk, so that was the interference because of the two openings. Now, we're going to talk about interference because of the one opening. And that is also called diffraction. And here is a video showing the diffraction pattern in a water wave, thanks to this Open
The next thing I
University.
want to look at is what happens to a water wave when it passes through an aperture. Well, I fitted an aperture here, but it's rather too wide for what I need at the moment. So if I fit these sliding doors, I can make an aperture that's about 3 centimeters across. And if you now look at the screen, you can see that as the waves pass through the aperture, they spread out. This spreading out of a wave as it passes through an aperture.
So opening is just that much. So the wave was something like this. Now once it exits that, it gets bigger, 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 and bigger. So that's what it's trying to show you. It's spreading. And now how this spreading changes when we change the opening, width of the opening, like a slit width. So let's watch that.
Is known as diffraction, and it's a property of all types of waves. So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave, more diffraction. If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced. And if I were to make the aperture very wide indeed, then there'd be hardly any diffraction. Well, I'm now going to return the aperture to its original width, and take a look at the effect of changing the wavelength of the wave. Now remember, I can change the wavelength by altering the frequency of the paddle using this control here. If I make the wavelength longer, you can see that the waves become more spread out beyond the aperture, more diffraction.
So wavelength is longer now compared to the more longer compared to this. So opening is smaller compared to the wavelength, right? So that's what it is saying. So smaller the wavelength, what happens? More spreading and so on. So anyway, so I think that's what it is showing us. Okay. So now let's look at this in terms of sketch. So this is like interference. See, we had an interference pattern like this. Now we have diffraction. What's the difference? There were two slits for the interference. Okay, so this was interference, we said, and two slits. And this one is only one slit, so single slit. So just like water wave were coming from the behind of that opening here, let's say light wave is coming, okay? Now, in this case, to analyze this, we can use similar equation, but in this case, what happens? Center has a maximum intensity and intensity decreases drastically. So the first dark happens to be over here, okay? And we had this equation for the bright fringes, m times lambda, and for the dark, we had m plus half lambda. Okay, now for the diffraction, we are writing for the dark fringes happens at m times lambda. But here you see there is this A, which is just the opening of one slit. So that changed here. So the right-hand side changed, the left-hand side also changed. And I think I have another drawing here to go with this. Okay. So you see, this is the opening we're talking about. So now, if we were to divide this into two portions and think about like a light coming from, one slit here, another slit over there, and then this distance would be just, d would be just a over 2, right? D would be a over 2. So what that means? So this d sine theta, when it is dark, for the dark fringe, we said, okay, it has to be m plus half and then lambda, right? And if it is for the very first dark fringe, for example, m is equal to 1, then this is going to be just half lambda. You see that? So m is equal to 1, it's going to be just half lambda, and d is half. So in this equation, what we are getting is d over 2, or a over 2, sine theta is lambda over 2, and this is for the first dark fringe. Okay. So now this 2 and 2, we can cancel that. And if we do that, then it becomes a sine theta is equal to lambda for m is equal to 1. And we can do the same math and come up with the 2 times lambda, 3 times lambda. So now the difference between, although the equation looks similar here, this is for the dark fringe and this is for the bright fringe, okay? Only that's the difference, but the equation looks similar. So when we are using similar equation for the diffraction, we are using that for the dark fringes only, where when we were using this for the double slit interference, then what happened was that was for the applicable for the bright fringes. So that's the difference. Otherwise, equation looks equivalent, similar. Okay, so let's not get confused there. Okay, so here is a question it says light from a red laser passes through a single slit to form a diffraction pattern on a distant screen. So let's say I'm visualizing something like that, taking advantage of previous drawing. If the width of the slit is increased by a factor of 2, so that means we increase that, what happens to the width of the central maxima on the screen? So here, you see that? So central maxima is the distance between two minimas. So that means if this distance here increases, that means we say, okay, this width of this one also increased. Width of the central maxima also increased, and so on. So if the width of the slit is increased by a factor of 2, so we have this. So for first maxima, I can write a sine theta is m times lambda, and this being first maxima, which is m is equal to 1, I can just write lambda there. Okay, we are looking for the width of the central maxima, so that means we are interested in this m is equal to 1 thingy over there. Okay, so now it says, okay, what happens to the width of the central maximum on the screen if the slit is increased by a factor of 2? So that means when a goes to 2 times a, what happens to the width? So here we can do the approximation. Okay, a theta is lambda, and it says red light. So what that means, a color has a fixed wavelength, so we're not changing the wavelength. So we have this equation from here to here, you know, for a small angle, let's say for a small angle. So now, right now, the angle is something like this. What happens when we double this size? Maybe I should draw something like this, right? What happens if we double that? So that's what this, when a goes to 2 times a, theta has to go what? To keep this lambda constant, when a goes to 2 times a, theta has to go half. When one increases, another one has to decrease by same proportion to keep this same. Okay. Okay. So now when I do that, what happens? This is same as that. So that means, so width of central maxima, yeah, decreases by half, decreases to half. So if you are thinking, okay, we are just looking at one side, see, this would be like, you know, other side is symmetric. So both side increases and decreases by the same proportion. And in this equation, A is basically this width here. Okay, so that's how we can figure out where these spots are. And these spots are, you know, this kind of experiments are useful actually to finding the wavelength. So if you can measure, let's say, this length here, and then, you know, what's the separation of these fringes are, and that means you can calculate the wavelength. So in experiment, actually, that's what you do. So let's suppose you discovered a light and you are not sure what wavelength of that light is, or you discovered an electromagnetic wave. You don't know what wavelength of that is. So you can set up experiment like this and figure out the wavelength. Okay. So that's all I have for the interference and diffraction. So for next class, they're not going to be pre-class assignment, but they're going to be weekly assignment. Next week, we are not covering new material. And they're going to be midterm, I think, next week on Thursday. Tuesday going to be review, if I'm not mistaken. Okay. Check the syllabus. Whatever day it's written in syllabus, on that day, they're going to be a midterm. Okay. So
Okay.
if you have quick question, feel free to ask, or else I'll see you next class.
I have a question.
Yes.
Can we come, like me and Zaina, can we come in person to your office hours to go over the right hand rules? Because like no matter how many videos we watch, like it's still not clicking sometimes.
So I'm not in campus these days.
Okay.
So that's why you cannot meet me in person on campus.
Should
Okay.
we ask like our lab TAs then? Like,
Certainly you can ask, but I'm not sure they will be helpful. And there are different version of right hand rule. Okay.
yeah,
So in the review, I'll talk about that
okay.
and I'll let you practice there. So if you have something like, pens, pencil, bring two of them. And
Okay.
if you also have something like this ring, bring
Okay.
that. Okay.
Okay.
That will be helpful to, practice. Yeah,
Okay.
unfortunately, I'm not in campus. Okay. Sorry.
Okay. That's okay.
Um, I guess the problem for me when it comes to the right hand rule is visualizing what's on paper in a 2D form. Is there any tips for that, or 3D, sorry?
So what's on the paper and how to bring that thing up in the real space from the paper, you are saying, from
Yeah.
this sketch to the real life. So that's why I asked you to, bring something like, these pencils, let's say at least two pencils, okay? And a ring, something like this, okay? Oop.
Okay.
And yeah, something like that, or something like that. If not, bring a cup. If you don't have that, bring a cup like that. We can also grab this one, right?
Okay.
So
Okay.
we'll talk more about that next class.
Okay.
Okay,
Thank
thank
you.
you.